Okay, let's start. So, in the last class, we looked at the telescopic cascode op amp. So, let me actually paste it quickly if it works. Yeah, okay. Yeah, so this is the telescopic cascode. So, again, okay. Yeah, so we still have the same old differential pair. The only difference is that we have a cascode in the NMOS side as well as a cascode in the PMOS side to boost the output resistance, right? And in this, okay, let me just reduce the size. Yeah, okay. Yeah, in this okay, telescopic cascode, what was the small signal gain? Huh? GM of which transistor? Yeah, M1 or M2, let's say M2. Oops, okay. Times, what is the output resistance? It was the parallel combination of the bottom cascode and the top cascode. So that is essentially GM4 R04 R02. Oh my god, in parallel with GM6 R06 R08, right? Cool. And in the last class we also saw the common mode ranges at the input and the output, and yeah, we calculated that. And one issue in this telescopic cascode is that when you put it in unity feedback like this, we saw that the range of voltages you can accommodate is really small, and for a simple example we saw it's around 350 millivolt or so. But of course in not all applications you will be doing this unity feedback connection, so in that case you will not be constrained by the fact that the input must be equal to the output. So in a general setting we will see what is the absolute maximum the output can reach and the minimum it can reach. So I believe we started with that in the last class. Let's resume. So to remind your memory, this was the ranges of voltages we saw we can have at the output. Okay, let me just close and open it and see if it works. Yeah, okay. No improvement. Okay, let's work with what we have. Sorry, yeah, okay. So this is the range of voltages. So now our goal is to find what is the absolute maximum and minimum we can have here. So let's say we start from the minimum side, and for finding the minimum we need to find the minimum we can apply at VB4. So tell me, if I keep reducing VB4, which of the transistors will have issues? Yeah, why? Yeah, remember that the current is fixed at I0 by 2 as long as the gate voltages are same. So which means the gate to source voltage is fixed. If VB4 drops, this voltage also drops, and since the gate is fixed, again this guy M2 will go out of saturation. And what is the minimum, what is the minimum the voltage VD2 can go to? Yeah, but remember that, yeah, that is same, but absolute minimum is drain to source voltage of the transistor M2 plus the drain to source voltage of the transistor M0. Again, for reaching that we need to apply an appropriate voltage here. Let's assume we are doing that. So in that case, what is the minimum we can have at VD2? Overdrive of M2 at a current I0 by 2 plus overdrive of M0. Okay, so this is the minimum VD2. So then can you tell me what is the minimum output? You know, this voltage is the minimum it can reach is so much. What is VB4 in relation to VD2? One gate to source voltage? Yeah, higher or lower? Higher. Okay. This is the source voltage. So this is the gate voltage. So just one VGS higher. So this is basically the same thing. The overdrive 0 at a current I0 plus the gate to source voltage of M4 at a current I0 by 2. Okay. Again, this should be clear if you observe the output, right? Output, the minimum you can go is the minimum VDS, which is overdrive of M4. Sorry. Okay, sorry. Yeah, hold on. Yeah, minus, this is basically, sorry, hold on. I made a mistake. This, yeah, hold on. Let me rewrite it here. This is what I have written is VB4 minimum, right? Remember, what I have done is this is basically the drain voltage plus the gate to source, that is VB4. So output is going to be one threshold smaller than that, right? VB4 minus VTH4 is the output. Okay. So if I subtract VTH4, how can you simplify this? It's going to be overdrive of M4. Okay. So let me write it also. So output minimum is going to be overdrive of M2 at I0 by 2 plus overdrive of M0 at a current I0 plus overdrive of M4 at a current I0 by 2. Okay. Is clear? So here again you see the minimum output you can have is drain to source voltage, which is overdrive of M4, plus drain to source voltage of M2, which is overdrive of M2, plus one more drain to source. And the important point to notice, this output can reach this minimum voltage as long as you can apply the appropriate gate voltage here, right? Only if you apply this VB4 minimum at the gate, the output can reach this minimum, right? Because remember, at the minimum side we are constrained by this gate voltage. Only if you apply this voltage, the output can reach this. Okay, that is something to remember. So similarly, what I'm saying is this is the minimum output can reach, but for this to happen, we need to apply this voltage at the gate of M4, right? Because remember that the constraint on output comes from the voltage VB4. Okay, so only if we apply a minimum possible voltage for VB4, you can reach the minimum possible for the output. Okay. Cool. So similarly, can you help me find out the maximum of VB6? If I increase VB6, what will happen? If I increase VB6, what can you say about this voltage? Again, source to gate is fixed because the current is fixed. So if you increase VB6, this will keep increasing. And ideally, of course, you want this to go to VDD, but you can't. What is the maximum we can have here? Right? So let me write that here. So VDD minus overdrive of M8 at a current I0 by 2. That is the maximum we can have at this drain. So which means, what can you say about VB6? Yeah, so VB6 max is basically one source to gate voltage smaller. So this is maximum of VB6. So maximum output is one threshold higher. So if I do plus mod VT at 6, how can you simplify this? Okay, here VT at 6. That is again another overdrive. Okay. So if I write it here, I'll have plus mod VT at 6. So that you can simplify to overdrive, so that V out max is VDD minus overdrive of M8 at a current I0 by 2. Again, you can again see from this output, ideally you wanted to go all the way to VDD, but that's not going to happen because you have to maintain a minimum source to drain across both transistors, and that turns out to be this. And once again, I want to highlight that this is possible because you have free control on what you can apply at VB6. Okay. So fundamentally, the maximum of output is limited by the gate voltage VB6. Since you have free control on the gate voltage, you can apply whatever you want to be the maximum and get this maximum. Okay, please remember that. Cool. So then I'll just explain one other thing related to this. Can I do this? Oops. So let me actually copy this here. Okay, cool. Let me also copy the telescopic cascode once. So now let's look at my minor variant of this. So what I'll do is the following. Yeah, so please recollect that we came to this telescopic cascode by first constructing a single-ended circuit and then put two halves, and then to convert to a single-ended output we decided to generate the bias voltage here, and that we did it by observing that if the current here is greater than this current, this voltage will increase, so we can basically go and connect it, right? But remember that I can also do it by comparing the current flowing here with the current flowing in the rest of the branches. So it means if this current is say greater than the rest of the current, this will increase. So I can as well go and connect gate and drain of M7, right? I guess this is this is one thing one of you had asked in the last class, so I can as well do this. Okay, right? Same thing. Is that okay? Similarly, I can generate VB6 also by doing a similar connection there. So that way all bias voltages are generated, right? So this looks simpler, and in fact this will also work. And here, can you tell me what will be the incremental, do you think anything will change in the small signal gain? What will change? Okay, think, right? Only change we have made is in this portion. In all our small signal calculations, be it the short circuit GM or finding output resistance, we essentially used only two information about this portion. Number one is the fact that this is a current mirror, so any current flows that gets mirrored. Same thing is happening in both of them. And the second thing is the assumption that the impedance looking up is smaller, so that the impedance looking into the source can be approximated as 1 by GM, right? And in fact, okay, maybe I can show it here. Right now I have something like this, right? So two of these things like this. So let's say I think M5 and M7. What is the resistance looking up here? 1 by? Okay, remember if I just have, okay, hold on, I'm drawing two circuits. Right, so let's get to that. So basically this impedance is 1 by GM. Everyone is fine. So basically remember that how many terminals I have in this network? Two terminals. So how many port network? One port network. Again, small signal, it is a linear one port. For linear one port network, how many parameters you need for characterizing? What is that? Resistance. So anytime you go and see this guy, you know that this guy is disguised as a resistor. That's all, right? So I can replace it by a resistor. Similarly, this is a resistor. That's all, right? So this is basically series combination of these two. Okay. So yeah. So again, even here looking up impedance is going to be small, and that is the only thing we used in the left half of the circuit. So nothing will change in the small signal calculations, right? You please go and work out. So it will be the same. Only thing that will change is the some of the large signal and DC operating points. Let's look at that. So first,
can't we connect VB4 to the drain of that M3?
VB4 to the drain of M3. Okay, try it out and check. Try it out and check. Let's discuss it in the next class. You think what will happen? Yeah. So first of all, can you tell me what is this voltage? I mean, this guy. What is setting that voltage? It is set by the gate voltage of M7. So that is going to be VDD minus source to gate of M7 at a current I0 by 2. So what is this voltage which I am marking here? The source voltage is known minus one more source to gate drop, which is VSG7 at a current I0 by 2, and then minus VSG of which transistor? VSG5 at a current I0 by 2. Is okay? This is same as the source voltage of M5. I am looking at the gate voltage of M5, so this is one source to gate smaller than that. So which means, what can you say about this voltage operating point? That should be same as this guy. Okay, leave it. So now let's quickly find out the maximum the output can take, whatever we did here, right? So again, if I keep increasing the output voltage, which transistor can have issues? M6. So what is the maximum the drain of this transistor can go? One threshold above the gate, right? So let me write it directly. The maximum output I can have is one threshold above the gate. And what is the gate? I mean, what is the potential at the gate? We have written it here, VDD, VSD7 at a current I0 by 2, right? Plus, right? This is this plus mod VTH. Again, I will say 5 and 6 are same, so I will replace it with 6. Okay. And similarly, 7 and 8 are identical, so I will just replace it with VGS8. Identical transistors for the same current, VSD is same. Okay. So how can you simplify this? VDD, the last term is the overdrive of M6, so that's straight away. And if I write it like this, overdrive of M8, so what is the additional term that should come? Minus VTH of 8. I've just simply rewritten the same thing. Okay. So now you compare the maximum you could get here and maximum you could get here. Which of this is higher? The left side is higher. Okay. So that's the main difference. With respect to small signal, everything is fine. This will have a higher output that you can achieve.
Also, when designing transistor going out of saturation, what do you think?
No, you should make sure it doesn't go out of saturation. So I didn't understand the
Range
question.
is very small, and so
Which range? This range. No, this is actually not so small. I mean, overdrive can be as small as, let's say, 50 millivolts. Let's say threshold is 400 millivolts. If you have a supply of 1.8 volt, it's reasonable. It's okay.
so what happens that sometimes VGS minus VTH comes in, so in simulation it comes very small.
No, VGS minus VTH, it doesn't come. You set it for something, right? If you have not designed for an appropriate VGS minus VTH, you will not get it. Gate to source voltage is set by the current and the sizes, right? You have to design it accordingly. Okay. Yeah, I mean, see, here also it might be tempting to say that the maximum output can reach is VDD minus, drain to source voltage of this minus drain to source voltage of that, right? But the main difference is you could do it here because the gate voltage was free for you to connect. That's why I was highlighting the point that for the output to reach this, VB6 has to be the maximum voltage that we computed earlier, right? Whereas here that VB6 is fixed here, so which means that's what you can get. Is the point clear? So for this reason, this portion here is often called the high swing cascode current mirror. I mean, remember that if I don't have this guy here, it is a normal current mirror, right? The moment I add this extra transistor, I am doing cascoding. I mean, this is also a current mirror with a cascode. Can have two variants of a cascode current mirror, but the one on the left provides a higher swing. That's all. Okay. Cool. So let's one minor thing. Let's look at continue. So here we know everything. So we just need to figure out how to generate these bias voltages. That's the last part. I'll show how we can do for VB6. One way in which you can generate VB6. Similar technique you can adopt for VB4. So first of all, let us say, let me go to this page. Yeah, notice that if the output has to be has to reach the maximum, VB6 has to be at this voltage. Okay. So it makes sense that we aim to bias VB6 to be at this voltage. Similarly, if output has to reach this minimum, VB4 has to be this value. So it makes sense you try to bias VB4 to be at this point. Right? So let's quickly see how one might generate VB6, which is this. That's correct. Yeah. Okay. Let me put it here. Yeah, let it be here. Or let me see, I can push it here maybe. Yeah, let me actually try to slightly rewrite it. So I'll rewrite it as like this: VDD minus VSG8 at a current I0 by 2 minus VSG6 at a current I0 by 2. Fine, same thing. Okay, so now can you suggest a way in which I can get this voltage? Or let's say start with a simpler thing. Let's say I want to get this voltage first. How can I get it? VDD minus source to gate of M8 at a current I0 by 2. Yeah, looks like that's a simple thing. So let's say I have a reference current of I0 by 2. So I can take a replica of the transistor M8. Do this. Keep the current source straight and connect. Right? I call it M8 prime, copy of M8. So this will generate this voltage. Now let us say I want to get this this voltage. One more source to get lower. This is VSD6. What can I do? You connect another, but what should be the transistor? Diode connected, but similar to 6. So this will give me VDD minus VSG8 minus VSG6. So this part is done. So I just need to get a voltage that is higher than this by one threshold. Or let us say I want to get a voltage slightly higher than this. Higher than this. Can you suggest a way? Huh?
If you have a transistor which has absolutely no current, then the gate to source voltage is like one threshold.
Okay. It's kind of there. We'll come to that. But let's say where will I do that also? Let us say you have some block which can give a. What is the simplest thing that can give a voltage drop? Resistor. Let's say you can put a resistor there. We'll come to what you told. It's an interesting thing. But where can I put a resistor here? Okay, maybe I'll just tell this. See, if let's say now I'm doing this, right? I want a voltage which is higher than this voltage. So logically speaking, do you think I should be climbing up this stack or lower? Up, right? So basically this point I know is this voltage. I want to get a voltage slightly higher. What can I do? So then if I tap from this point, that will be higher by I0 by 2 times R. Right? Remember, this point is set to VDD minus VSG6 minus VSG8. That is this potential. So which means this one will be higher than this by I0 by 2 times R. Right? Of course, this will work, but again, the issue is you can't make sure that I0 by 2R is exactly equal to your mod VTH, because threshold voltage keeps changing with voltage, temperature and process. So then can you suggest a way in which I can get a drop approximately equal to threshold? What did you say?
You can have a
Let me copy this.
there's absolutely no current, like
Okay.
minimum current, then the gate.
So you are saying that I can have a MOSFET with absolutely no current. Why is that? Why do you think that will be equal to threshold?
Because the gate to source voltage will be near
Okay.
the threshold.
If I have a constant current, what is the gate to source voltage? In terms of the transistor, huh?
Threshold plus the volt, right?
Yeah, I mean in terms of the transistor properties.
VTH plus under root 2I
Under root 2i
given 6W over L
plus VTH, right?
that can drive.
Now you are saying that you will tend I to 0 and that will make it approximately threshold. Very good observation, but the problem is I have a current of I0 by 2, right? But this is a good starting point. Is there some way in which I can make this approximately equal to VTH besides keeping the current small? W is under your control, right? So if I have a very large W by L, which means gate to source voltage, okay, fine. So now instead of a resistor, you can go and put a transistor like this. Okay, which has a very large W by L, right? So this will be the voltage, gate to source voltage across it will be approximately equal to the threshold, right? Huh? I mean, depends, right? If you ideally if you want it to be exactly the threshold, you have to tend it to infinity. But of course, you can't go it. So keep as large as possible if you want.
Shouldn't that be NMOS? Shouldn't that be NMOS?
No, but if you have an NMOS, how will you do it?
Because the bottom thing is fixed to VDD minus 1 VSG minus 1 VSG.
Correct.
And we need a one threshold voltage higher.
Higher, right? So it should be source should be higher, right? This is the gate.
There is a drain here.
No, this is the gate. Gate and drain are shorted for the PMOS, and the source is higher than that, right? Okay, yeah. Okay, I should have explained it. So basically, now this will be the okay. So remember, this point is VDD minus VSD6 minus VSD8. That is same as the gate voltage for this transistor. We are tapping from the source. So this will be one source to gate higher, and the source to gate voltage is approximately the threshold voltage if you have a very large W by L, right? Again, this is not the only way in which you have to do. Again, this is just one way, right? You can think of multiple ways.
So we have large W and then in layout can be.
I mean, that's what, right? I mean, we'll come to layouts later, but the thing is, you can have large W by L. How large? That's the next question. We'll address it later. Again, see, other thing is now remember that this branch is existing only for generating the bias voltage. So we don't have to burn the same current I0 by 2 as we are burning here. So what can you do?
You can size up the transistor.
No, I mean, you can size down. Let's say I scale it down by 1/10. So all the transistors will be 1/10 smaller, right? So okay. I want to maintain the same gate to source voltage. That's the whole idea. If I scale down the current and I scale down the width also appropriately, nothing changes. Okay. So this is something you can do so that the bias branch doesn't carry unnecessary current. Okay. Cool. So then let's move on. Again, similarly, you can think of a way in which you can generate this VB4. You can follow similar approach. I'll give that as an exercise. Okay, so then let's move on.
Sir, we are using that current source, so basically there will be a transistor over there.
Yeah, I mean, assume that for your design, you'll get one reference current externally. From there, you mirror all the currents using current mirror.
1/10 of that current. So this means that we need to give a higher VGS for that transistor. That will be limited by.
No, okay, okay. The question is, okay, let's say you have a reference current of I0 by 2, I0 by 20 given or something, right? Let's say you do this, and then I can size this transistor 20 times W so that the current here is I0, right?
Okay, so you are given smaller.
Yeah. You'll have a reference current and you size up the transistors accordingly to generate any required current. Huh?
We can step up the current, but
Yes.
not step it down because then we'll need a higher VGS.
No, you can also step it down. For example, if you want it to be even smaller, you can have a smaller width, right? If let us say this is I0 by 20, you want I0 by 40. If this has a width W by L, use a width of W by 2 by L, right? You can just play with the widths in a proper ratio to get the required scaled versions of the current. Cool. So yeah, so bottom line with the telescopic cascode is that we have a very high gain, but one issue is if you try to put it in unity feedback, as we saw in the last class, the swings you can have is limited. So that is one issue. So now we'll look at another.
Sir, if you reduce the current by 110,
Uh-huh.
sir, then won't the current also be affected of the same branch?
Correct.
VSG will be like current of 100 by 20.
No, but if I size the transistor also at 1/10, if I reduce the W also by the same factor, then VSC doesn't change, right? This is the expression for gate to source voltage. I scale the current and scale the width also by the same factor, nothing changes. Right? In fact, we'll see later, everything finally depends on what is called the current density or the ratio of current by width. This has to be fixed for a VGS to be fixed.
So, what was the requirement of scaling that current? Can you repeat that?
I mean, okay, you can have I0 by 2, but unnecessarily you are wasting current, right? The existence of this guy is only to support this guy, right? So you don't want to be wasting power here. In principle, I don't need this at all, right? I mean, if magically this is available to you, it's good. Okay.